Hello guys, and welcome back to the PyTorch tutorial series. In the last couple of videos we have seen the basic workflow in PyTorch, and from this video onwards we're going to be implementing simple models using the PyTorch framework. So we're going to start with linear and logistic regression, and as we continue we're going to implement more complicated models such as convolutional neural nets and RNNs. In this video we're going to talk about linear regression, and it's one of the simplest and most familiar kind of regression model. So before we define what linear regression is, first let's talk about the concept of regression. The main purpose of regression is to predict dependent attributes from a set of attribute variables. And in the regression problem, the output variable can be real or continuous value, such as salary, weight, or area, and etc. We have different types of regression. This can be a simple linear regression model, a polynomial regression, support vector regression, decision tree regression, and random forest regression. So basically regression is made up of two basic components. The first one is the dependent attribute, and this is a variable that is dependent on other set of attribute variables. And what makes it a regression is that the output dependent variable will always have to be a real or continuous value. So in machine learning there are two types of problems. The first problem that we could solve using machine learning is a regression problem. So whenever you want to predict a continuous value, such as the next, for example in a stock market, if you want to predict how the stock is going to perform over time, that could be one regression problem. Another thing could be salary. So regression problems are all around us, and it's up to us to use what kind of regression model that could be suitable to solve that specific problem. So before we move on to linear regression, let's see some assumptions that we should consider about the linear regression algorithm. There are 4 assumptions associated with a linear regression model. If these assumptions are violated, it may lead to a biased or misleading results. The first thing that we need to consider is the linearity between the dependent variable and independent variables. So the linearity concept just says that the relationship between the independent variables and the dependent variable has to be linear. If not respected, regression will underfit and will not accurately model the relationship between the independent and dependent variables. So if we want our model to do better on solving regression problems, the relationship between the independent and dependent variables has to be linear. As we can see from the first image, or from the first graph, we can see that the regression line is mimicking the distribution of data, because the relationship between the data points mimics a linear relationship. So this regression line is actually increasing because it has a positive slope, or the data distributions may have negative correlations. So the line can have a negative slope, as we can see from the second plot, or the data distribution may not have a linear relationship, so we need to use some complicated regression models such as polynomial regression in order to mimic the data distribution. So we will have more of a hyperbolic function to mimic the data distribution. So when we consider linearity, in order to use linear regression model, the data distribution has to mimic a linear path, or the relationship between the independent and dependent variables has to be linear. Otherwise, our model will underfit the data. If there is no linear relationship, various methods can be used to make the relationship linear, such as more complicated transformations such as polynomial and exponential transformations for both independent and dependent variables. Second assumption that we need to consider about the linear regression model is normality. And normality is just normalizing the data distribution before we fit it into our model. The model residuals should follow a normal distribution. Residual is just a concept that describes the difference between the predicted and actual data values. If the distribution is not normal, regression results will be biased, and it may highlight that there are outliers or other assumptions being violated. So if we don't normalize our data, there might be a lot of outliers from our data distribution, and it will be very hard, or our model will actually be influenced by those outliers rather than mimicking most of the data. So the second task has to be normalizing the data before we use the linear regression model. So we need to correct large outliers in the data and verify if the other assumptions are not being violated. So a normal distribution will have to mimic the standard normal distribution graph, and most of the time it's between 0 or 1, or between -1 and 1. The third assumption that we need to consider for a linear regression model is independence, and each independent variable should be independent from other independent variables. So the variables that we are predicting are those that are called dependent variables, and the variables that we are using to make the prediction are called independent variables. And independence is saying that the relationship between these independent variables should be mutually exclusive, or one independent variable should not be dependent upon other independent variables. Multi-collinearity is when independent variables are not independent from each other. So multi-collinearity is when these variables are dependent on one another, and if they're dependent, that means they could just be used as part of the prediction and not part of the set of independent variables. It indicates that changes in one predictor are associated with changes in another predictor. So if there is a relationship between each independent variable, it means that changes in one predictor might influence other predictors. So we can use heat maps and calculate what is known as the VIF, or variance inflation factors scores, which compares each independent variable's collinearity with other independent variables. So we can describe the relationship between each independent variable by using a heat map and we call this the multi-collinearity of features, and this heat map represents values ranging from minus 0.5 up to 1. So the more related these independent variables are with one another, then the heat map will give us a red output, and if they have less similarity or dependency on one another, then we can get a darker or maybe lighter set of colors that we can see from the legend or the label. And we can test this using the Durbin-Watson test for autocorrelation. So this is a test that we perform in order to see the autocorrelation between independent variables, and this formula uses residuals, which is the current residual minus the previous residual, and we take the square and take the summation and divide it by the summation of the square of the current residuals. We don't need to worry about the intricacy of this formula or the independence problem in detail. We just have to know that we can use that we have to assume that all the independent variables that we use for linear regression model has to be independent of one another. Another assumption that we must consider is what is known as homoscadacity, and it's just a fancy word for equal variances. So the variance of a residual is the same for any value of x. So residual, as we have described before, is the difference between the actual and the predictive value. And the model does not fit all parts of the model equally, which leads to a biased prediction. So homoscadacity is one type of problem where we could have equal variances, and the model will not be able to mimic the distribution of the data, and it will lead us to a more biased prediction if we have equal variances. And it can be tackled by reviewing the predictors and providing additional independent variables, and maybe even check that the linearity assumption is respected as well. So there are other concepts known as heteroscadacity, which is the inverse of homoscadacity. It's a mouthful word, so it's very hard to actually pronounce the word, but we can just use it to describe equal variances. So if there is equal variance or a difference between each data point, then we call the concept as homoscadacity. And if it is different, if the variance or the difference between each data point is different from one another, then we call it heteroscadacity. And we can use a test known as Brusque-Pagan for testing the homoscadacity of the data distribution before we use the linear regression model. So basically we need to consider around 4 assumptions, which are linearity, normality, independence, and homoscadacity before we use a linear regression model. So if we think that the data distribution requires a linear regression model, then we need to consider these 4 concepts before we move on and start using the linear regression model to solve that problem. So in order to solve the final assumption, which is homoscadacity, we could provide additional independent variables, or we could check the other assumptions which might lead to the problem of homoscadacity. Finally, after we have considered all of the assumptions that could be useful for using or selecting the linear regression model, let's see what linear regression model actually is and define the term linear regression. Linear regression is a machine learning algorithm that is used for prediction. And in this current world of uncertainty, we need to predict certain things to keep things on track. For example, the sales marketing manager wants to know the demand for drugs, taking into account all seasonal variations to help the drug manufacturing companies. This is one use case where we could implement the linear regression model. I also gave another example of predicting the stock over a certain period of time. That's also a regression problem. So whenever you have some dependent variable that is continuous over time and you want to predict it, and the data distribution mimics a linear path, then you could consider using the linear regression model to predict the next set of outcomes. So linear regression is just identifying the relationship between the variables and representing that relationship using a straight line. So this is a key word when considering the linear regression model, that the data distribution has to mimic a straight line. Otherwise, we might have another set of linear regression model known as multiple linear regression. So a simple linear regression is or it uses a single feature or one independent variable to model a linear relationship with a target or one dependent variable by fitting the best straight line to describe the relationship. So what we call the linear regression model is just a simple linear regression model where we could use a single independent variable to predict an output, and beta naught and beta 1 just represent coefficients, and epsilon represents the error, and y hat is the predicted output. So in linear regression, your primary objective is to optimize your predictor variables in hopes of predicting your target variable as accurately as possible. So if you cannot solve that problem by using simple linear regression, another solution might be using multiple linear regression. For example, if you have a bunch of independent variables instead of one, or multiple independent variables from x1 up to xp, then you could use a more complicated function in order to mimic the data distribution. So you're gonna increase the number of coefficients you have in order to make your model more complicated. So next, let's see the key components for a linear regression model. If you have a simple linear regression formula which is given by mx plus b, or it could be given by this representation where we have a y-intercept b naught and a slope of b1, x is the independent variable and is the error. And here, by using all of these components, we can predict an output y, which is called the dependent variable. So these are some terms that we must memorize or understand before we start building a linear regression model. So the dependent variable y is a variable that is being estimated and predicted. It is also known as target, a target variable. The independent variable x is an input variable which is also known as predictors or features, and the coefficient is a numerical constant also known as a parameter. So the parameters from our models that we have previously discussed are just represented by b1 and b0 in terms of a linear regression model. So all of the coefficients that we use in the linear equation are going to be our parameters that we are going to optimize our model. So the intercept, the y-intercept b0 and the slope b1, or in this case m, determines the angle of the line, which determines the angle of the line are the parameters that we need to optimize. And the intercept is different from the other set of coefficients that we use for the independent variables because they are constant. They are constants used for determining the value of y when x is given as 0. When all the independent variables are 0, then we can get the y-intercept. So another term that we use for a linear regression model is a cost function. We have discussed this in detail in the previous video, but let's just summarize what kind of cost functions that we use in order to solve linear regression problems. Cost function provides us with the best possible values for the parameters b0 and b1 to make the best fit line for the data points. It is also known as the mean squared error, and we change the values of b0 and b1 so that the mean squared error value is settled at the minimum. So the primary reason that we use a cost function is so that we could minimize it by using an optimizer. And the residuals that we have discussed before are the differences between the predicted output and the actual label. And the mean squared error is just the summation of all of these variances and divided by the number of samples. So this is generally the mean squared error cost function, and our task is to minimize this cost function so that we could better estimate the parameters such as b0 and b1. The next important terminology to understand linear regression is gradient descent, and it is a method of updating b0 and b1 values to reduce the mean squared error. So one way we could minimize the cost function is by using an optimizer algorithm such as gradient descent, and we have covered this in detail in a previous video. And the idea behind this is that to keep iterating the b0 and b1 values until we reduce the MAC to the minimum value. Now, once we have covered all of the key components used to construct a simple linear regression model, finally we need to find a method that would help us to determine the line of best fit. So if you have a data distribution and it mimics a linear path, how could you find a line that approximately mirrors the path of the data distribution? Or in other words, could we have some kind of metric that could evaluate how well our model is performing with respect to the data distribution? So the purpose of the loss function and the optimizer is that we could minimize the difference between the actual and the predicted value from the model, and so we take the difference between the actual label and the predicted value for each of the data points, and once we use an optimization algorithm such as gradient descent to find the best set of parameters, we could find the best representation or line that fits our data points. So one set of metrics that we could consider to find the line of best fit is the R-squared, or what is also known as the coefficient of determination. R-squared is just a statistical measure that is used to assess the goodness of fit for a regression model. It uses a baseline model that finds the mean of the dependent variable y and compares it with the regression line. So in order to explain this easily, we can use this diagram for the R-squared explanation. So there are two terms that we basically need to consider in order to evaluate the R-squared term. The first one is the residual sum of squared errors, what is known as the RSS. It's known by a bunch of names. You can represent it by using RES or SSE, or in this case RSS, which is the term on the numerator. And it's basically the sum of the square difference between the actual y and the predicted y. So the sum of residual squared errors is just finding the difference between the actual and the predicted output, which is also known as a residual, and squaring that term and takes the summation. Then we will find the sum of residual sum of squares. So for each data point, we have to find the variance or the difference between the actual and the predicted output, and then sum them together after squaring the difference. The second term is what is known as the TSS or TOT, which is the total sum of squared errors. It is the sum of the square difference between the mean of y and the predicted y. So the mean of y is actually different from y fitted, as we can see from this diagram. Y mean means finding the mean of all of the y's. So here we're representing the x and the y-axis. So after finding the mean of all of the data points, then we can find the difference of the mean and each data point. So if this is the mean if this is the mean for all of the data points, which is represented by y mean, then we can find the difference between each data point and that mean, and then after squaring each term we can find the summation, and then we call it the total sum of squared errors. That is going to be the term in our denominator. So the R squared is just the difference between 1 and, after dividing these two terms, which are the RSS and the TSS. So the main purpose of the R squared function is it uses a baseline model that finds the mean of the dependent variable y and compares it with the regression line. So it finds the mean of the dependent variable y, and then it compares it with the regression line. So we might find a different regression line at different points when we come up with a different set of parameters. So R squared is a function that's used to select the best line of prediction that could mimic the data distribution. So after evaluating the R squared term using the previous formula, let's see what the actual values of R squared represent by using different scenarios. R squared can take a value between 0 and 1, where values closer to 0 represent a poor fit and values closer to 1 represent an almost perfect fit. So if you have an R squared value of 0%, that means the model fails to explain any variance. So the primary purpose of the R squared function is just to evaluate the variance between the data points. And if you have an R squared value of 0%, what that is saying is your model is failing to explain the variance between the data distribution. On the other case, if you have an R squared value of 100%, which is 1, then your model explains all the variance. That means your line is actually fitting the data points exactly as they are. And this kind of model will actually not be that beneficial because you wouldn't find a scenario in which your line fits all of the data points. But sometimes it might happen and it seems great, and 100% representation of all of the data points. Another case might be that the R squared value will be 40%, which means that the model explains only 40% of the variance, so it is a reasonable performance. Or you might get an R squared value of 80%. In this case, the model explains the bulk of the variance when compared to 40%. So what we can learn from this is that the R squared value can help us to select the line of best fit, and a higher value of R squared means that our model is performing really well, and a lower value of R squared means that our model is actually underfitting the data. That's all for this video, and starting from the next video we will see the implementation of the linear regression model using Jupyter Notebook. And thank you for watching this video, and don't forget to like and subscribe. Audio Jungle.